All right, so we're talking about how to solve line integrals of functions. F of x, y, z. And we're going to write out the steps for how to do this, but kind of like the one thing to always remember is parameterizing curves is the overall approach. I'll write out the steps for what that actually means, but when in doubt, parameterize curves if you need to find a line integral. So a line integral of a function is going to look one of two ways. You're either going to have integral over some curve C, f of x, y, z ds, or it can alternatively be written integral over C, f dx plus g dy plus h dz. These are both the same thing. They're just represented in slightly different ways and solved slightly different ways. But your first step is gonna depend on your curve C, so it doesn't really matter what form it's represented in. And you're going to parameterize the curve C the way we learned how to parameterize curves way at the start of class in terms of some variable t for time. And so what you should have is some like list of equations, x of t, y of t, z of t for t bound between certain values that describes your curve C. That's what the first step would have given you. So 2, just check that you have that and make sure that you have all these items in order. In your function, f or fgh, so this part right here or these 3 parts right here, replace all variables x, y, and z with parameterization x of t, y of t, z of t from the second step. Actually, we'll do the check after step 4. And then what you're going to do is you're going to replace your ds will either be x prime of t squared plus y prime of t squared plus z prime of t squared dt. Oops. Or that's for the first one. Or if you're given dx, dy, and dz all separately, what you're going to do is just take each of those components separately. So dx equals x prime of t dt, dy equals y prime of t dt, and dz equals z prime of t dt. And so whichever one of those two matches the equation you have, you're going to go ahead and replace these so that they also depend on t. And so your fifth step is just check that only t is left inside your integral. If you have any x's, y's, or z's left over, then something went wrong and you need to go back and see what you didn't plug in. And then using the a less than or equal to t less than or equal to b, the bounds of your parameterization, when you set up your curve C, you're just going to change the bounds of your integral to run between those values. And so the final form of what you're looking at should either be integral a to b, some function that depends only on t, times x prime of t squared plus y prime of t squared plus z prime of t squared dt, or for the second one, a to b f of t x prime of t dt plus g of t y prime of t dt plus h of t z prime of t dt. And before we only wrote over one curve C, f dx, g dy, h dz, but now that this is sort of three different dt's, you can go ahead and write them ab like that, or you can add them all up and evaluate them together. Doesn't really matter what you do. And then once you have it in this form that only depends on t and has bounds informed by your curve C, then what you're going to do is evaluate it. This is a 1D integral. It's something that you learned before this semester started, and so you should be able to do it. The hardest part here really is this identifying the parameterization, making sure that you have x, y, and z, and bounds for t in order to plug everything in. Once you plug it in, it's a very simple, Calc 2 type problem. And so we're going to go ahead and do some examples next up so that you can see these two different forms kind of in action.